Okay, what I did till now was, in unit 1, the only algorithm design strategy that we have discussed is decrease and conquer. It is characterized by the problem of size n is decreased by a constant 1 or 2 or k. How do we contrast divide and conquer with decrease and conquer? What is the difference between these two strategies? Whereas in decrease and conquer, the problem size or the input size is decreased by a constant. In divide and conquer, it is decreased by a factor. If the input size is n, let's say it is decreased by a factor 2. So we have, or n by 4, n by 4. For example, that corner covered tile problem, the problem is divided into 4 sub-problems, each of size maybe n by 4. And the sub-problem sizes are almost equal. If it is n by 2, this is also n by 2. They need not be exactly equal, but roughly equal. We say that the sub-problem sizes are balanced. That is the fundamental difference between decrease and conquer and divide and conquer. Consequently, in decrease and conquer, every call will result in only one recursive call because there is only one subproblem. Whereas in divide and conquer, one problem may be divided into 2 subproblems or may be divided into 4 subproblems and so on. Therefore, one call to the algorithm will result in 2 recursive calls or maybe 4 recursive calls. These are the 2 main differences between decrease and conquer and divide and conquer. Difference number 1, for decrease and conquer, the instance size is reduced, decreased by a constant. Whereas for divide and conquer, it is reduced by a factor. 2, in decrease and conquer, one call results in only one recursive call because there is only one sub-instance. Whereas in divide and conquer, one call to the algorithm may result in multiple recursive calls. We call that tree recursion. Whereas this is linear recursion. Decrease and conquer and divide and conquer are algorithm strategies. Recursion or iteration is not a strategy, it is a technique. Look up the dictionary for the difference between these words: technique, tactics, and strategy. The course is about algorithm design strategies, not about techniques or tactics. You may immediately ask a question. Okay, in decrease and conquer, we deconstruct an instance into one subinstance. In divide and conquer, we deconstruct the instance into 2 or more subinstances. In the extreme, we may deconstruct the instance into every possible subinstance of a problem. That extreme way of decomposing or deconstructing or dividing an instance of a problem into all possible subinstances and then construct a solution from the sub-solutions will be called exhaustive search. So in the algorithm design strategy spectrum, decrease and conquer is at one end of the spectrum. Exhaustive search is the other extreme end of the spectrum. In exhaustive search, a problem, an instance is divided into all possible sub-instances in order to construct the solution. Whereas in decrease and conquer, an instance is divided or reduced to one sub-instance. Okay, now let us go on. Don't read the slide, that is for notes. Wherever important, I will point out. In a divide and conquer algorithm, to solve the given problem, decompose an instance into a small number of sub-instances. The small number may be just 2 sub-instances or 3 or 4. The sub-instances are balanced in size. That means their sizes are roughly equal. I say roughly equal. They need not be strictly equal. Very important is a small number, not just one. Solve each of the sub-instances, combine the sub-solutions into solution of the given instance. That is the crux of divide and conquer algorithm design strategies. What is the work done by a divide and conquer algorithm? There is a typo. Divide and conquer. Or what is the running time of a divide and conquer algorithm? A divide and conquer algorithm does two kinds of work. This is a recursive call. This is another recursive call. Okay, for example, if it is f of n, this is given f of n by 2, this is given another f of n by 2. So the work is done, certain amount of work is done by call itself. Then there is work done by recursive calls. The work done by call is distributed as follows. Or what is the work done by the call? The call does work in order to deconstruct the input into sub-inputs. The call should also do some work to combine the sub-solutions into solution. So work done by the algorithm in dividing the instance into sub-instances, that is one part of the work, and combining the sub-solutions into solution. This is the work done by the call. The other part is the work done by recursively called algorithms. Every recursive call also does some work. Suppose the input size is n and the instance is divided into a sub-instances. Each sub-instance is of the size n by b. It need not be n by a. Why it need not be n by a? Because the instance itself, the call itself does some amount of work. The work done for decomposing and combining, let it be n to the power c. In general, it is f of n, but this is a common case, therefore n to the power c. Thus, the work done by the algorithm that takes an input of size n is t of n is equal to every recursive call does t of n by b, n divided by the factor b amount of work, and there are a recursive calls or a sub-instances, therefore this is a times running time of n by b plus the amount of work done by the call itself, that is n by n to the power c. We have already seen this divide and conquer recurrence and how you can solve that using recursion tree. The result of solving this recursion, the divide and conquer recurrence, is captured in the master theorem, as we have already seen. It may be, there are three cases, big O of n to the power c or big O of n to the power log of, I forgot, a to the base b, and the other is big O of n log n. There are three cases. Now for quicksort, let us read that out. Your input is an array such as 1n19640385. Select any of the elements in the array, let's say 5. All elements less than 5, bring them to the left of 5. For example, 1 is less than 5, 4 is less than 5, 0 is less than 5, 3 is less than 5. In the same order, 1, 4, 0, 3. All elements greater than or equal. 9 is greater, 6 is greater, 8 is greater. So, this is the basic step. Choose an element arbitrarily, then partition the array into two subarrays. The subarray to the left of this element is less than the element 1403. The subarray to the right of the element is greater than or equal to this element. This element is called pivot or splitter because we are splitting the array. We say that the array has been partitioned. Left subarray, pivot, right subarray. Left subarray is less than the pivot. Right subarray is larger than or equal to the pivot. Note that the left subarray need not be sorted. 1403 is not sorted. 968 is not sorted. But the pivot has come to its final position in the sorted array. If you sort 1403 and if you sort 968, then the whole array is sorted. While doing that, note that the position of 5, the position of the pivot, the index of pivot itself will not be affected, will not be altered anymore. So with one partition, the pivot is brought to its final position in the sorted array. So the basic idea of quicksort is choose any arbitrary element as the pivot, partition the array or list into a left subarray, a smaller subarray, smaller than the pivot, and a larger than or equal to subarray, larger than the pivot, and then sort the smaller subarray and sort the larger than or equal to subarray independently. The idea is captured here. The pivot has come to its final position in the sorted array. Sorting each of the subarrays can be done independently of each other. Okay, now I am tracing the idea of quicksort. I denote input by red and maybe output by green. 1964035. 5 is the pivot. So it partitions into smaller subarray, pivot, larger subarray. 1403 is the input to a recursive call. I am always selecting the last element of the subarray as the pivot. Here 5 is the, I am selecting 5 as the pivot. I am selecting 3 as the pivot. It need not be so. You can choose the first element, last element, any element. I said arbitrary. Okay. The smaller subarray is 1, 0. The larger subarray is 4. 1, 0 will be the input to another recursive call. Partition. 0 is the subarray. The larger than or equal to subarray is non-empty. Look at that. The smaller subarray is empty. When the subarray is empty or has a singleton element, it is sorted. If the input is an empty subarray, the sorted output is an empty subarray. If the input is a singleton, the sorted output is also singleton. Okay. And let's come here. Okay, this is a singleton, therefore this is sorted. Similarly here, 968 is the input, 6 is the smaller partition, 9 is the larger partition. Now, 6 is a singleton, 9 is a singleton, therefore 689 is the output. Similarly here, 1 is a singleton, therefore 01 is sorted. When these two calls return, this one, the recursive call with 10 as the input and the recursive call with 4 as the input returns, it is 01 on the left side, 4 on the right side, and the pivot. When these two recursive calls return, or if you want, we could have also written this as 1, 9, 6, 4, 0, 3, 8, 5. 5 is the pivot, 1, 4, 0, 3, 9, 6, 8. Then here, 3 is the pivot, 1, 0, and here 4. Then here, 0 is the pivot, 1. And then you may say they combine to 0, 1, and this combine to 0, 1, 3, 4, and this combine to 5. And if you follow that, it will be 6, 8, 9. This is yet another way of tracing the quicksort call, quicksort algorithm. So the quicksort algorithm itself is very easy. Quicksort, A is a list, input list A of comparable items, output a new list which is equivalent to sorted A. Input is 1964038, output is 01345689. It's a new list consisting of all the elements of the input, only that the new list is sorted. It is a recursive algorithm. Any recursive algorithm should have at least one base case, 2, a recursion step. What is the base case here? We said that if A is equal to empty list, the output is also empty list. If A has a singleton, the output is also a singleton. This can be written as if the length of A is equal to 0 or the length of A is equal to 1, then the output is the same as the input. If length of A is equal to 0 or is equal to 1, which is the same as saying less than or equal to 1, then output is also A. This is the base case. Choose any element as the pivot. I am using this notation A at 1 to n. In the last time I taught algorithm, I followed this notation. 0 to n means A at 0 and so on. A at n minus 1, n is not included. This is the notation followed typically by most of the popular programming languages, including Python. This would mean A at 1 to A at n. This time I have decided to follow this notation for various reasons. I am not following this notation. But when you write programs, this is what you have to deal with. Okay, pivot is A at 1. We split the list into two parts, roughly equal in size. Smaller or equal, the other is larger, or smaller and larger are equal. I am using a kind of mathematical notation. For all x in A from 2 to n, because I have already taken out A1. If we have removed A at 1 from the list A, we are left with A at 2 to n. In the list A at 2 to n, all x, all elements which are less than or equal to the pivot, make them into a smaller sublist and call it smaller or equal. In the same way, for all x in A at 2 to n, for all element in A at 2 to n, if the element is larger than the pivot, collect them into another sublist and call that larger. Then quicksort, the smaller or equal sublist. Quicksort, the larger sublist. In between, put the pivot. That is the result of, that is the output of the whole thing. So there are two recursive calls. This is called list comprehension in Python and other functional programming languages. In Python, you will write that as, okay, for all x, for x in A 1 to the end, if x is less than or equal to pivot. This is how you will write in Python. This algorithm will work. Even though it is inefficient, this is basically quicksort, and if you write the program in Python, this works. But we don't want to implement quicksort using lists. We want to implement quicksort using arrays.
Sir, I have a doubt, sir.
Yeah.
So in this case, when you say A 1 to n, we are saying the first element is A of 1.
Yeah. In my notation now.
Okay, sir. So we are taking the first element to be the pivot.
Yes.
Okay, sir.
You can take the first element as the pivot, or last element as the pivot, or median of the first element and the last element as the pivot. Any random element is the pivot. It doesn't matter. The algorithm works.
Yes, sir. Yes, sir.
Okay. Homework. Um, this is called Polish national flag. I think this is Polish national flag. Red and white. Generally, we state the algorithm as follows. You are given an array of buckets 1 to n. In each bucket, there is either a white ball or a red ball. Okay. And there is a robo. The robo can do only two operations. The robo can inspect the color of the ball. That is operation 1. Operation 2 is the robo can exchange or swap the balls in two buckets. Write an algorithm so as to bring all red balls together at one end and the remaining white balls together at another end. This is 1, this is n. Let's say 1 to I minus 1 is all red, and I to n is all white. I hope the problem is clear. Okay. Basically, suppose there is an array of zeros and ones, or positive numbers and negative numbers. Rearrange the numbers in such a way that all zeros occupy one subarray and all ones occupy another subarray, or all negative numbers occupy one subarray, all positive numbers occupy one subarray. In our case, instead of red, I would say all numbers which are less than the pivot. Instead of white, I will say all number which are larger than or equal to pivot. So my red is equivalent to less than pivot. My white is equivalent to larger than or equal to pivot. Bring partition the array in such a way that the subarray 1 to I minus 1 has all the numbers less than the pivot, red. And the subarray I to n has all the numbers greater than or equal to the pivot, white. Take 30 seconds and write this algorithm. Then we will proceed. I have shown you the trace of the algorithm. For example, okay, the trace of the algorithm is only this. Okay. 5 is the pivot. This is the input. And this is the output. The input array is 1864039. The output is a partition into two subarrays. One subarray consists of 1403. The other subarray consists of 689. This subarray, the red subarray 1403, is less than the pivot 5. The green subarray 689 is greater than or equal to the subarray. Suppose they are numbered 1, 2, they are indexed 1, 2, 3, 4, 5, 6, 7. Okay. The red subarray is from 1 to 1, 2, 3, 4. And the green subarray is from 5 to 7. What should the algorithm return? I may say the algorithm will return 5. The algorithm returns I, then 1 to I minus 1 is the smaller subarray, and I to n is the larger subarray. You can write the algorithm now. If you have done, please let me know.
Sir, I think I have an answer.
Can you share your screen? We would like to. We would all like to see that.
Oh, should I type it out, sir?
Oh yeah,
Okay, sir. Give me a second, sir.
yeah. If anyone else can show you have an algorithm, I would like you to share your screen. While he is typing. Similar to Polish national flag is another algorithm called Dutch national flag. DNF. Instead of two colors, there are three colors: red, blue, and white. Okay. You have to partition the array into three subarrays. 1 to I minus 1 is red, I to j minus 1 is white, and j to n is blue. Take it as a homework. So Polish national flag is a much simpler. Partition the array into only 2 subarrays. Dutch national flag partition the array into 3 subarrays. This Dutch national flag is at the heart of another famous algorithm called select the kth minimum or smallest number in an array. Very important algorithm. Select the kth minimum or select the median of an array of numbers. This is a very important algorithm. The algorithm is basically Dutch national flag. So at some point I may ask it. I will assume that you have studied and implemented Dutch national flag algorithm. Are you ready?
Sir, just a second.
Yeah.
Okay. Sir,
Yeah.
I've just written it out, sir. I haven't written like a full algorithm as such.
It's fine. It's fine. No problem. I'm not expecting a perfect, finished, polished product. Your
Yes, sir.
thoughts. Yeah.
So we are choosing an arbitrary element, sir, and this is under the assumption that there are only two colors possible, red or white, and there is an element present in the array at that index.
What is that? What does that mean?
So let's say we get an array of size n. All n elements are having an element. See,
Yeah.
or all n indexes have an element.
Yeah.
So once we choose an arbitrary element, we can inspect it and we can determine whether it is red or white.
Mm-hmm.
So since there are only two possibilities, we choose that, and essentially we take it like the pivot for our Polish quicksort. Uh, then we it's exactly like quicksort, but if our pivot is red, then if the next inspection is red, we'll keep it in left. If it is white, we'll put it to the right subarray. And after all the quicksorts are performed, we need to return the position of pivot.
I appreciate your attempt.
Yes, sir.
Yeah, but maybe I was wrong in first introducing quicksort, and then in order to do quicksort, I said we have to select a pivot and partition the array into two subarrays, a smaller subarray and a larger than or equal to subarray. Maybe I shouldn't have started like that. I should have said, oh, okay, we have a problem. The problem is we are given an array of white balls and red balls. We just want to rearrange the red balls and white balls in such a way that all red balls are together and all white balls are together. Oh, maybe you should turn off the mic. Yeah,
Sorry, sir.
no problem, no problem. So if I had started like that, then your thinking, your line of thinking would have been more streamlined and you would not worry about quicksort. So I wanted to do that without worrying about quicksort. Oh, in the future, my partition algorithm will be made use of in quicksort algorithm. You should not have that burden at all. Maybe I made the same mistake again. When I told you about Dutch national flag, I said, oh, this Dutch national flag, instead of two subarrays, it partitions into three subarrays, and this algorithm would be useful in selecting the kth minimum in an array of numbers. I should not say that. Okay, we have two standalone algorithms. One is a two partition algorithm, the other is a three partition algorithm. I have no intention to use these algorithms anywhere else. How would I write the algorithms? It is a simple,
Sir,
yeah.
I haven't typed it out, but can I try explaining my the way
Yes.
I see it?
Yeah. Yes, madam.
Yeah. So basically, like you give the pivot as the input, like probably 5 for this,
Yeah.
and like you read each element of the array, and suppose it's less, like probably if it's less, it's red, and if it's greater, it's green or whichever color combination. So if it's red, how do I say, like suppose you read it, or like you read the first element and it turns out to be less, so you give it a color red. And then if the next element is like greater, so you go, and then like if after a greater element you find out a lesser element, you swap it with the greater element, kind of a thing. like uh
I
like
understand,
how
madam. Yeah.
yeah
I see your heart.
yeah, so like you swap it, and so in the end, like all the lesser elements come on one side. Like you basically, like if the first, if you have a lesser element after a greater element, only then you swap. It's
Yeah.
something like that kind of a thing.
Fantastic. You are right on the spot. Maybe I only need to train you guys to how to reason about algorithms more concisely is all that is missing. Otherwise, you have an idea. You have good idea. Okay. Generally, this array based uh, algorithms, I have my way of explaining with a little diagram.
Sir,
Yes, sir. You have
sir,
some thought? Yeah.
I've typed it out, sir. Can I share?
Yeah, sure. Most welcome. I am, in one sense, it is boring for me, for myself, to take all the time to keep talking.
Can you see, sir?
Oh, yes.
I've chosen the last element as the pivot,
Mm.
and I've kept another variable k. It's the last element of the left side of
Yeah,
the
yeah, yeah.
left partition, sir.
Yeah, I think the basic idea is right. I can see that. Even though the details I did not check, from the for, if, and the final swap, I can see it is a partition. Good. That's the idea. What's the name?
Nestor, sir.
Nestor. Okay. Thank you, Nestor. Great. Uh, we scan the elements of the array from left to right one time. If we do that, the elements that we have read, I call them historical input. The elements that we have not yet read or scanned as the remaining elements. With the historical input, I say 1 to I minus 1.
Sir, we are sharing anything, sir?
Oh, mine is not shared? Okay. Yeah, okay, fine. Is it shared?
Yes, sir.
Okay. Let me say this is all less than the pivot. Somewhat, it has the property red. And then I will say I2 j minus 1 is greater than or equal to the pivot. Let me say this is okay. This is less than pivot. Green. Greater than or equal to the pivot. Okay. And this is the gray area. This J to N. This is the scanned or historical input. This is the remaining input. So after some time, I would have read elements 1, 2, 3, and so on up to j minus 1. And somehow I have partitioned them into 1 to I minus 1, less than the pivot, I to j minus 1 greater than or equal to the pivot. Now I am considering jth element. So the historical input grows by 1. I want to maintain this loop invariant. 1 to I minus 1 should always be less than or equal to less than pivot. I to j minus 1 should always be greater than or equal to p, and I also want to grow it. So as she explained and as Neston, right, explained, there are only 2 cases. If this is red or this is green, oh no. All I have to do is this I to j minus 1 should be expanded to I to j, because I to j minus 1 is already green, j is also green, therefore I can expand or let grow I to j minus 1 subarray to I to j subarray, which is still green. So the scanned subarray has expanded. At the same time, we also maintain the loop invariant. Suppose it is red, then the element j should not be a part of the green subarray, it should become a part of the red subarray. How can I make the part of the red subarray? If I swap these two, 1 to I minus 1 is already red. Now I also becomes red. Formerly, here we had a green. So after swapping, this will be green and this will be red. So 1 to I minus 1 is expanded to 1 to I. It is all red. And green is shifted to I plus 1 to j. Maybe I need to draw a few more diagrams. So let me say this. Case 1. The item at j is equal to green. All I have to do is increment j to j plus 1. Case 2. The item at j is red. What I have to do is, I have to say swap the items at I and j, and then I have to increment both. I becomes I plus 1, j becomes j plus 1. That's it. That's the crux of the algorithm, and that is what I have written here. Algorithm partition. For want of time, I am just explaining the basic idea. I would like to spend really more time, but time doesn't allow. Partition A. In most of the algorithms, I will not assume A is from 1 to n. Why should I put that restriction? I will always put A from low to high. If I write the algorithm to work on a subarray A low to high, I can always make it work on A 1 to n by passing 1 for low and n for high. But if I hard code it for 1 to n, I can never make it work for any subarray. So this is a good programming technique. Whenever possible, when the parameter is an array, make it work on a subarray. All right. A low to high is a subarray of comparable items. Output index I such that A low to I minus 1 is less than the item at I, which will be the pivot. I plus 1 to high is larger than or equal to I, pivot. All right. And this is the loop body. There are 2 cases. A at j is green or A at j is red. That is, A at j is less than the pivot or greater than or equal to the pivot. If it is less than the pivot, what should we do? Swap the items I to j and you should say I becomes I plus 1 and j becomes j plus 1. Else, what should you do? J becomes j plus 1. This j becomes j plus 1 is common to if clause and else clause. Therefore, I factor it out. Whether the condition A at j is less than the pivot is true or false, j becomes j plus 1 will always be executed. Therefore, I have taken it out of the if clause and the else clause. When I take it out of the else clause becomes empty, and therefore there is no need to write the else clause. This is the loop invariant. All the time, load to I minus 1 here. Load to I minus 1 is less than the pivot. I to j minus 1 is greater than the pivot. Okay. Make sure that the loop invariant is true here also. Li is true here. Check it. I will ask such questions in the CA test. Is the loop invariant true before the loop starts? When the loop terminates, j should be equal to n. Then we have n or high, whatever it is. If this is high, we have partitioned it to low to I minus 1 and I to high. So until j is equal to high, if you are writing while, you should write while j is not equal to high. Since j starts with low, sometimes you also write j is less than high. Anything is okay. Okay. So with that, we have partitioned the array. But we do not only want to partition the array, we also want to bring the pivot to its right position, which is achieved by swap a I comma high. I am using the last element. The element that index high is the pivot. Low to I minus 1 is less than the pivot. I to high is all larger than or equal to the pivot. I want the pivot to lie right in between the smaller subarray and the larger subarray. Therefore, I am swapping the contents of the elements at index I and index high. After this, the pivot is at position I and return I. This is almost over. It is time. With this slide as the last slide, we can wind up. Algorithm quicksort a low comma high, input an array a low to high of comparable items, output a is a permutation of a and a is sorted. It is a in place sort. The inputs and outputs are, the input is an array, the output is the same array in which items have been rearranged, numbers have been rearranged. Contrast this with the first quicksort algorithm that I suggested. It worked with lists. Input is a list, output is a new list. It is not the same list which is in place mutated. All right. So this is testing for the number of items is equal to 0 or 1. If the subarray low to high has no item or one item, there is nothing to do. It is already sorted. That is a base case. If it is larger than 1, then partition the subarray of A from low to high. Pivot is that I. After returning from partition, low to pivot minus 1 is less than pivot. Pivot plus 1 to high is larger than or equal to pivot. Okay. Therefore, all that we have to do is sort the subarray low to pivot minus 1. Sort the subarray from pivot plus 1 to high. So one recursive call results in 2 recursive calls with input size strictly smaller. We have removed one element from the array. Therefore, both the inputs will be strictly smaller than A low to high. Check the conditions for correctness of a recursive algorithm are satisfied. All right. So in this class, we have presented quicksort algorithm. What is divide and conquer? Quicksort is an example for divide and conquer. Merge sort is also an example for divide and conquer. And there is a host of algorithms. We presented quicksort using quicksort algorithm and also another algorithm for partition. Take time to understand the algorithm by taking an example and tracing how quicksort works on the example that you have taken and also how partition works on the example you have taken. Very important. To ensure your understanding, trace the algorithm on examples. This is one of the popular questions. I give you an example and ask you, trace how the algorithm works on this example. We stop here and tomorrow we will analyze the running time of the algorithm quicksort.